Somewhere in the universe right now, there is an object so massive, so dense, that if you stood next to it, you wouldn't even have time to realize you were dying. Light itself can't escape it, time slows down near it. And it has been eating everything around it for billions of years. We call it a black hole. But here is the question almost nobody asks: is there a limit to how big these things can get? Can a black hole just keep eating forever, growing endlessly until it consumes everything? Or does the universe somehow put a leash on these monsters? The answer involves some of the most extreme physics in existence. And it turns out the universe has a surprisingly elegant system for keeping black holes in check. Here is how it works. Real quick, let's make sure we're on the same page. A black hole is not a hole. It is not empty space. It is a region where gravity is so overwhelming that the escape velocity exceeds the speed of light. Nothing, not matter, not radiation, not information, can get out once it crosses the event horizon. Black holes form when massive stars collapse in on themselves at the end of their lives. All that mass crushed into an infinitely small point called a singularity. But the black holes that really matter cosmically, they're a different breed entirely. At the center of almost every large galaxy in the universe sits a supermassive black hole. Not large, not really big. Supermassive, our own Milky Way has one. It is called Sagittarius A star. Mass 4 million times our Sunday. That sounds huge. It is not the biggest. The black hole at the center of galaxy M87. The one we photographed for the very first time in 2019. 6.5 billion solar masses. Sagittarius A tilde 4 million solar masses, M87 asterisk. Tilde 6.5 billion solar masses. Ton 618, tilde 66 billion solar masses. cited scale check, ton 618's event horizon. The point of no return is larger than our entire solar system. If it replaced our Sunday, Earth would be deep inside it, not orbiting it inside it. So, how big can these things actually get? Turns out there is a ceiling, and the physics behind it is genuinely fascinating. Astronomers have been wrestling with this question for decades, and measuring black hole mass isn't easy. You can't exactly point a scale at one. You have to infer it indirectly, watching how nearby stars orbit, how gas moves around the center, how light bends as it passes nearby. Lots of uncertainty, lots of estimation. But here is what the numbers say. The largest black holes we've actually observed sit in the range of several tens of billions of solar masses. Theoretically, some models push the upper limit to 270 billion solar masses. But in practice, most experts agree that finding a black hole larger than 50 billion solar masses in the real, current universe is extremely unlikely. Theoretical max, tilde 270 billion solar masses, practical limit. Tilde 50 billion solar masses, ton 618. Tilde 66 billion solar masses, weight. Ton 618 is already at 66 billion, and the practical limit is 50 billion. Is the universe already breaking its own rules? Not exactly, but it is complicated. And the complication lives inside something called an accretion disk, the most violent, most beautiful structure in astrophysics. Here is the thing most people get wrong about black holes. You picture a black hole as a cosmic vacuum cleaner. Stuff falls in, disappears. Done. The reality is way more dramatic. Most material doesn't fall directly into a black hole. It spirals, like water circling a drain, except at a significant fraction of the speed of light. The incoming gas and dust form a massive spinning structure called an accretion disk. Inside that disk, material is moving so fast and grinding against itself so violently that temperatures reach billions of degrees. We're not talking about hot. We're talking hotter than the core of a nuclear explosion. Every single. Second, at those temperatures, the disk radiates ferociously X-rays, gamma rays, ultraviolet light. A blinding torrent of radiation blasting outward in all directions. And here is the critical part, that same radiation that the black hole's feeding frenzy creates. It pushes back against incoming material. The black hole is essentially generating its own force field. The harder it tries to eat, the more radiation it creates, and the more that radiation repels the next meal. Think of it like trying to eat while simultaneously blowing everything on your plate across the room. The universe built a feedback loop directly into black hole feeding. And then there are the jets. The powerful magnetic fields in the accretion disk can take some of that infalling material and fire it in two tight beams, relativistic jets, blasting out from the poles at nearly the speed of light, extending for thousands of light years. Material that was supposed to feed the black hole gets shot back out into the universe instead. The monster is eating, and simultaneously returning what it can't digest back to the cosmos. This feedback loop has a name. It is called the Eddington Limit, named after British astronomer Arthur Eddington, who first calculated it in 1916. The idea is simple. For any given mass, there is a maximum rate at which it can consume matter before the outward radiation pressure exactly balances and then overwhelms the inward pull of gravity. Cross that line, and the accretion disk blows itself apart. Material gets ejected. Feeding stops. The black hole starves itself through its own appetite, but here is where it gets more interesting. The Eddington limit can be broken. In the early universe, when galaxies were forming and the density of available gas was orders of magnitude higher than today, black holes could undergo what is called super-Eddington accretion. They ate faster than the limit technically allows. Briefly, violently, and that is probably how some black holes grew so enormous so quickly, in a universe that was only a few 100 million years old. Eddington limit, radiation pressure equals gravitational pull super-Eddington, possible in early, dense universe current era. Mostly Eddington limited growth. This also explains something that has puzzled astronomers for years. Why do we find absolutely monstrous black holes in the very early universe, when there supposedly wasn't enough time for them to form? Super-Eddington feeding during chaotic, gas-rich, early conditions. The universe broke its own speed limit when it was young. And now, James Webb is making that puzzle even more complicated. Since launching in 2021, the James Webb Space Telescope has been looking deeper into the early universe than anything before it, and it keeps finding black holes that shouldn't exist yet. Massive, fully formed, supermassive black holes in galaxies that are less than 1 billion years old, when the universe itself is only 13.8 billion years old. Even with super-Eddington accretion, the math is incredibly tight. Some of these objects would have had to start growing from almost nothing and hit hundreds of millions of solar masses in a cosmically tiny amount of time. Current JWST findings, several black holes discovered at redshifts above Z7, meaning we're seeing them as they existed less than 800 million years after the Big Bang, already exceeding 1 billion solar masses. Standard formation models struggle to explain this. This is not a crisis for science. This is science working exactly as it should. A new observation that doesn't fit the model means the model needs to be updated. Maybe there are seed black holes from the very first stars that were larger than we thought. Maybe dark matter plays a role we haven't mapped yet. Maybe super-Eddington accretion was more common and more extreme than current models predict. We don't know yet, and that "we don't know yet" is one of the most exciting phrases in all of science. Step back and look at the big picture for a second. Black holes are the most extreme objects in the universe. They consume everything within reach. They warp space-time itself. They can outshine entire galaxies when feeding, and yet galaxies are stable. Ors has been spinning for 10 billion years. The stars haven't all been eaten. The gas hasn't all been consumed. The solar system exists. We exist. That stability isn't an accident. The same feedback mechanism that limits black hole growth, the radiation from accretion disks, the relativistic jets, also regulates star formation across the entire galaxy. When a black hole eats too aggressively, the energy it releases heats up the surrounding gas, suppressing new star formation, reducing the food supply, and eventually throttling the black hole's own growth. The black hole and the galaxy co-evolve, each one regulating the other. A dynamic equilibrium that has kept galaxies structurally stable for billions of years. If black holes could grow without limit, if the Eddington feedback didn't exist, galaxies would likely have been consumed long ago. The conditions for planets to form, for life to emerge, might never have stabilized. The universe's limit on black hole growth may be one of the reasons anything exists to observe it. There is something almost philosophical about all of this. The universe creates the most destructive objects imaginable, engines of consumption that devour light itself. And then it writes physics into the fabric of reality that keeps those engines from running unchecked. The universe is under no obligation to make sense to you. Neil deGrasse Tyson. But here is what I think is even more remarkable. The universe doesn't just make sense. It makes elegant sense. The same physics that creates a black hole also creates the mechanism that limits it. The same accretion disk that feeds it also starves it. The same gravity that makes it dangerous also makes it part of a system that produces stability that is not coincidence. That is the universe operating on deep, consistent principles that we're only now beginning to fully map. We don't know the true upper limit of black hole size. Ton 618 at 66 billion solar masses already challenges our models. James Webb keeps finding objects that shouldn't exist yet. Every time we think we've drawn the boundary, the universe shows us something on the other side of it. And that is not a failure of science. That is science doing exactly what it is supposed to do, following the evidence, updating the models, and marveling at a universe that keeps being more interesting than we expected. So, how big can a black hole actually get? The physics answer, the Eddington Limit, accretion disk feedback, and the finite supply of available gas create a practical ceiling somewhere around 50 to 70 billion solar masses in the current universe. The honest answer, we're not entirely sure. Ton 618 is already at 66 billion. James Webb is finding black holes that break our timelines. The theoretical maximum is 270 billion. A number we haven't tested, the real answer. The universe is more extreme than our current models capture. And every new telescope, every new observation pushes the boundaries of what we thought was possible. In the grand sweep of cosmic time, black holes are the universe's most extreme editors, consuming the old reshaping galaxies, regulating the conditions under which stars and planets, and eventually life can exist. They're not just destroyers, they're part of how the universe organizes itself. And the fact that we, tiny, brief, carbon-based creatures on a pale blue dot orbiting an average star, can look up and figure this out, that is the most remarkable thing of all. If this changed how you think about black holes, the next video goes even deeper, what actually happens inside the event horizon, and whether the laws of physics as we know them completely break down. Hit subscribe so you don't miss it. Drop your biggest black hole question in the comments. I read every single one. See you in the next one.